Nej, jag tyckte det var... Ja. Ja, du tyckte det var gott.
So is LISE, someone named LIS, was that you? Okay, so, okay, because he's the real wizard.
Okay, I just defined something closer.
Oh, okay, you were just in the wrong direction.
Great. Jag blir så stor. Jag blir så jävla otrolig. Alltså, så blir det.
Ja, men verkligen så här. Man kan inte se.
Fast man blir så orolig.
Men vadå, så han måste ju ha köpt
Ja, men alltså... Tillsammans med att han träffar ju Alex också. Han gillar ju jag gillar ju nej, alltså i högskolan. Ja.
Vadå, så han blev tjock av honom?
Han blev jättetjock.
Oj, vad är det som är då? Oj,
Gud vad många dokument jag har.
jämställdhet på...
Jaha. Vilken vecka är det?
Det ska inte så dricka.
Okay, it's 13:15. Let's get started. So we are streaming live on YouTube now. I think the screen should be at full resolution, unlike the last couple of times. So I wanted to remind people about assignment 2. So these are all, the autograder is almost complete, so most of you have done well, but maybe in the next several hours, I'll have the individual assignments done. It's getting quite tricky for me to give sort of human-in-the-loop feedback on the summary that you've written. So that's what I'm at about 318 lines of Python code to write the autograder right now. But I'm not very good at Python, so it's taking a while. But you have the solutions already, so you should know how well you did. Assignment 2 is posted. So what I'm trying to do, like I'm Raz, right? I don't know Swedish, right? And I don't know Swedish culture. I mean, I don't. So the culture in the classroom is basically like sort of New York, okay? So I grew up in sort of Midwest in New York, and it's cosmopolitan. Like so all of East and West Coast, it's fine, right? That's the culture. So if I say something and it offends you, and or it's confusing, or you don't understand, then just come and talk to me, because it's just a jazz, right? So the course is kind of a feedback loop, because it's designed like that, so that I can calibrate it to what you guys need, right? Otherwise, it'll be like maybe too mathematical or too sort of, I don't know. So that's why I'm embedding assignment problems like after figuring out what you guys feel and blah, blah, blah. So for example, in assignment 2, what I'm asking you to do is, give me some statistics like time to complete this problem in minutes, right? There's a specific one. And when you go take breaks and like watch YouTube and all, minus those times, right? Because I'm trying to get some kind of a difficulty level gauged for the exam questions, you see? So you have to kind of be serious when you do it, or at least do the subtractions. So then I can kind of calibrate it. I mean, my general principle or philosophy, or not philosophy, whatever, is I just want almost all of you to pass, right? So that's number 3, right? 3 points out of 5 points, right? So it should be like, you have to really go out of your way not to do that, right? So assignment 2 has only 0, 1, 2, 3, and 4 problems, right? So it's more difficult than assignment 1. And of course, I can make it more and more difficult, but I don't want it, they're spread across different difficulty levels, not necessarily in the first one being easy or hard. And I'll see how much time you take and how you do to kind of do the third assignment, and especially the sample exam. Is that making sense? Okay. Yeah, so then I also want to have a rough idea of how much time you guys actually are able to spend on courses, because typically, I don't know in Sweden, but in New Zealand and the US, engineering programs are professional programs. They have very hard schedules. Not as bad as doctors, but it's pretty intense. So students are usually like, so I don't want you guys to work too much, right? But so just the HP breakdown, I'd like to have an idea so that yeah. So anyways, fill in your person number. That's very important. Otherwise, I can map it to your grade. Yeah. So for example, assignment 2, problem 0, right? This problem is actually embedded somewhere in the lecture notes. So what you should ideally do is to have, at least notebook 5, 6, 7, and 8 open as tabs when you work on this assignment. That's exactly the setup for your exam. So you'll have tabs 0 through 11 open, right? And even the sample exam if you want. So there'll be 0 to 12, so 13 tabs maybe. So, and then you want to kind of get used to moving between them, right? That's the idea. So this assignment is sort of supposed to prepare you for it. So then before jumping directly into the assignment, I would sort of advise you to get the updated versions of 5, 6, 7, and 8, and then look at where these problems are embedded, right? Then you will get the context. Because I've kind of added a little bit of content, yeah?
When did you last update 5, 6, 7, and 8?
I don't know, like 4 minutes before I came down. Oh, but for the assignment, it shouldn't matter, right? I updated like 09 now.
Okay.
But then when I push updates, I'm pushing all of them for some technical reasons, okay? But the ones that don't need to change won't change. So you can find that out like this. So let's see, it's a good question. So if you go to, because I mean, it is a bit annoying, right? Because Raz is changing all the time. Yeah, I would hate it too. So I'm with you on that, right? So I don't know, let's go here and hunt down. This course, I think. Okay, so if you go, the easiest way to look at it is to just go to the Github repo. So this is not for normal, but this is mostly for developers. This is how I would check it quickly. So this is your course, Applied Stats 2019, Jupyter Notebooks, and then, if you look at it, it says here 3 days ago, 23 minutes ago. This is today's stuff I just did. Yeah.
It's a bit problematic when you do a U-try,
yeah.
have an answer, and then you update the...
Yeah.
Because then you don't have the answer.
Yeah, I agree with that. That is really annoying. So, well, I'm glad you're doing U-try. I'm very happy about that. But, I mean, the U-tries are like kind of to get you like walking a little, right? It's to make you brave. So if you kind of override U-tries, it's no biggie in a way, because you can try again. I mean, because what I mean by, it'll make you sort of strong. So that's not the point. Unfortunately, this time I'm giving it, I have to have feedback loops, right? Because I learn, I see how people are looking at me, I just try to embed contents in the right way. And so unfortunately, yeah, but the nice thing is the assignments will actually be much more contextualized now. Yeah. So yeah, so I don't know. Yeah, some of these things haven't changed, but you don't need to go here, you know, it's just, I mean, what I recommend is just to have like the current version or something, because it's not a lot of gigs. I mean, it's a light, you know, it's lightweight, right? It's a lot less than a little movie, so you can just have a refreshed version where all the updated stuff is, and you can have like a version you muck around. All right. Yeah, you shouldn't go here, you know, so because this will kind of get you confused. So anyway, here is, let me go back to assignment 2. So are there any sort of questions that are ambiguous about assignment 2? Something that's not clear. Okay, everything is crystal clear. I answered like maybe only 5 emails this time, which is awesome. The first assignment was like so many emails. So either people are afraid to ask me or they're all just really good. I don't know. So I also have open office hours from 3 p.m. To 5 p.m. today. So you're welcome to come and ask questions then as well. All right, so I'm supposed to cook at home tonight, so I gotta go at 5. All right, so this is our sort of very important topic now. Okay, yeah?
Yeah, I was just wondering, because I think the notebooks are really long.
Oh,
It
right.
takes a lot of time to go through them.
Yeah.
Like, how are you supposed to, if you want to go through them all, how are you supposed to know what to skip? And like, because if you try to understand.
Well, I don't think you should skip much because it's not like a textbook. I mean, Wikipedia is what you should skip, right?
Yeah.
So I'm compressing quite a lot there. I recommend to read it at least once. I mean, and I'm sort of trying to illustrate the concepts today, if I can start lecturing soon. So I'm going to tell you the main ideas, right? But then you need kind of a little bit of details to recalibrate it. Yeah.
And can I just ask, so in the assignment,
Yeah.
you said we were supposed to have like 82 hours. I know you said just now that we shouldn't have had or whatever, but still, like, what are we supposed to have had been doing?
Well, I really don't know. So this is okay. This I don't know. Like I just know some rules people tell me. So I know that is it 1.5 HP is 1 week of full-time study, right? The government loan, whatever. New Zealand has the same system, right? So 40 hours translates to so much support from the taxpayers. So that sort of usually in any sort of model, you map that hours into your course plans. So that I knew a lot about it in other countries I've taught. I don't know. So I just am guessing. And then I talked to someone who puts the same information in your assessment for the courses. She agreed it's the same. It's just that they rephrase the question in the assessments differently. That's all.
Yeah, but it's more like I feel worried since I don't know what's going to be on the test or whatever.
Yeah.
That I should have learned more than I have. So even though I've been on your lectures and the labs and read some of the notebooks on my own, I still feel like I don't know if I should have studied more. Like usually on our courses we have like assignments. This is an assignment, and we have the U-tries, but like even more so that we can study at home. Okay. I don't feel like I know what I should have been studying at home. Is it your plan or intention that we should just like listen, read through it, do the U-tries, and then we're on the
and then so if you did all this, you will find out before midnight this Friday how quickly you can do assignment 2. Assignment 2 is a bit more challenging, I think. Where's Maria? No. Is Maria here? Okay. Oh, yes. So she's the student rep. So is this more difficult than assignment 1? Assignment 1 was just not really anything, right? It was just to like.
I didn't say that it was. I meant that it was like we have 3 assignments.
Yeah.
So based on that, when you said that the assignments were going to be like
equal grades, yeah.
So what I meant was just that it definitely
right.
grade 1 assignment.
Yeah. Yeah, I mean, assignment 1 was like, I explained this already. It's quite complicated because the labs were not allowed to be given at the times I wanted them to be given. So we are working with a lot of constraints. The teaching assistant does not know the language that's being used. So, it's like, and I don't have, a standard camera system like in New Zealand. Like it's an operating environment I'm doing my best at, right? But the point is I want it to be calibrated for you guys, right? Because you are my students. So just, if you don't, today we should get into this because this is fairly subtle concepts now, right? So let's get into the lectures. Okay, so I already went through the outline last time, so we're basically going to look at the idea of estimation and likelihood and the parameter estimation in models. And then we really want to keep this philosophical distinction between what is a model, what is the observation, and what's sort of real life and all of this while we're doing inference, right? So this is proper statistics now. So the way we will understand the likelihood function is using our favorite guy, Bernoulli theta random variable, because all the concepts are already here. And then I'll get into the log likelihood function and introduce the very generic estimator, right? Estimator is, we'll formalize it. Its job is to take the data and find a guess for the true parameter that the data is coming from, right? The true parameter dictating the law, the distribution, from which the data is a realization of, okay? So that's the game. So we will probably stop at New Zealand Lotto data. Let's see how it goes. So then we actually use a real world data. Initially, we will use a simulated data just to get the ideas down. And then we will actually use a real world data. And then what I want to do is to give you like a maybe 10 minutes or so crash course on using Sage Math for basic algebra and calculus. This is what like high school kids in France and Germany are using. Sage Math is a very popular program all over the world, by the way, right? This is like introduced at high school levels all over the world. So, and why do I want you to do that? Because I want you to be able to do symbolic expression evaluations for maximum likelihood estimators. So in this course, I'm more interested in testing your concepts and the use of the machine to process data. Not so much in being able to quickly derive some, simple, well, maybe slightly more complicated algebraic manipulations, right? Or calculus-based manipulations. It's good to do some by hand, but pretty soon problems will become so complex, you have to resort either to symbolic machinery, which we will see, or more complicated machinery for which you have to fall back on your scientific computing course. We probably won't go there here. We're running out of time. So in an exam, I'll give you a problem, and then you can do it by hand if you want to find the maximum likelihood estimate, which we'll see soon what it is, or use the symbolic machinery. And then we will start looking at New Zealand earthquakes, as I said, with some intertime occurrence processing, and use this exponential lambda random variable. So this I summarized last time, so let me quickly do this again. Regression is a general problem, okay, where our goal is to estimate something as a function of some other things, okay? So these some other things are called explanatory variables. They explain this thing of interest, right? This thing is called a predictor or target variable or labels in machine learning. It comes with all kinds of names, but there's a y and there's a bunch of x's, okay? So we observe x's. So the game is, given the x's, I make a model for y, and this is essentially my estimator in a more general sense. And then comes new observations that I don't know about. That I don't know about in the sense, I know the x's, but I don't know the y. And my job is to figure the best y for the x I see. So that problem is an application of estimation, and that's called prediction, right? That's the second part. So I'll just touch about the ideas in prediction, because the first thing you will learn in statistical machine learning is prediction. So you will start from estimators and jump into prediction, because machine learning and computer science has been more focused on serving their users, right? So they're really much more into prediction, but it's just an application of estimation. We'll also get into correlation and causation. So my current plan is to do regression toward the last couple of lectures, I mean toward the end, okay? Because I want to go to something else, the next notebook called non-parametric estimation and confidence in hypothesis testing. Once we do those, we will come back to regression. It'll be a lot faster to do regression after those. Okay, and here is the big 3 bullet points about estimation. We have point estimation, set estimation, and hypothesis testing. Last time I briefly mentioned point estimation. So this whole notebook is about point estimation. It's essentially about producing a single best guess of some unknown quantity of interest. Maybe the parameter that's dictating the model. Maybe the click-through rate of some customer with certain demographic or historical clicking behaviors, in a targeted advertisement setting. Doesn't matter, but it's always a single best guess. Okay. Set estimation is different. So here we are trying to guess a set, right? Actually, a set, it could be a rectangle, whatever. A set that traps this quantity of interest at a very high probability, right? So it's like you're throwing a net in this space of things of interest. You're trying to hunt some true fish or true parameter, and then this net or whatever will capture it with very high probability. So that's called set estimation. Confidence intervals you've seen before are in this world, okay? That's to catch a little point in the real line of interest. And then this naturally leads to hypothesis testing. So I briefly mentioned this before. So we will set up, for example, a null hypothesis we want to reject, right? Likelihood is so important because it comes into regression. So classification is basically a prediction problem of regression, where say you're trying to classify an email as spam or not spam, right? So your labels are discrete, yes or no, or it could be finitely many, right? It could be, so these are called classification problems, which you will do in statistical machine learning in detail as well. And then in general, we have this principle called risk minimization. So that's the mathematical statistical principle or empirical risk minimization behind all of this machine learning and AI since the 70s, right? So there you simply use the data itself, you hide part of the data, you don't let the algorithm see it, and then you use this hidden part to justify your estimator, right? Justify the fit. So that's called empirical risk minimization. And then all Bayesian methods, so Bayes, where the Bayes rule plays a fundamental role, statistical and machine learning methods are called Bayesian methods. There, Bayesians are dead without the likelihood function. So it's a very important idea. Okay, so today, this worksheet is all about just this kind of estimation called parametric estimation. The other kind we will see is non-parametric estimation, right? So parametric estimation is when the parameter is in a finite dimensional space. So one other thing, like sort of on a philosophical note, you need to really bear in mind, especially with your STS students, right? Your sort of intersection of all these disciplines, is to really know that, mathematics is just a language, right? You're just expressing something very clearly, and it has a lot of assumptions. And one of the major assumptions is, even in inference, is that we have to really separate what's a parameter, what's a model, and what is sort of real life observations, and what does it really mean. Right? So, here I'm just sort of telling you we have, even for a simple coin toss, like some Bernoulli thing, we can say that the unknown bias of the coin coming up heads theta is not known. But then, maybe in our model for a fair coin, we will say theta is half, okay? So it's a very specific parameter we are choosing. And that's how we are choosing to model the outcomes of a fair coin. So how many of you completed watching the video from Stanford by Diaconis? It was like 8 minutes, no? So, in the video, he shows you these parameter ranges, right? How quickly a coin turns and how high it goes. So it's a sort of a PDE model. So there is actually a parameter range where if you give enough energy in the right way, the difference between landing heads and tails become very small. So that's the parameter range where you start modeling coin tosses, right? So if you are there and you do this stuff, even in a machine, what you need to understand is that the probability model is just a model for the observations by our own assumption, okay? So whenever we talk about true parameter that's behind the data, it's true parameter up to the model being explicitly assumed, okay? So this is the same thing. We'll come back to exponential and other random variables soon. So what I would like you to sort of, so maybe if you read this after my blabber, it'll make more sense. So I'm not going to read all this. But two important quotes I'd like to bring to your attention is one by George Edward Pelham-Box. He said, all models are wrong, but some are useful. This is very important, right? So you're Raazesh students one day, so don't forget Box's quote. The second one I really like, he's one of my heroes, Lucien Lacam. He was at Berkeley, he's also a statistician. He said, the only math I did not use is the one I did not know. So anyway, so what is the likelihood function? So the likelihood function is formally, the word just is English, right? How likely something is. And it's explicitly different from probability, right? Probability is an axiomatic thing. This has a definition too. But so the idea is something like, we have some observations, say x1 through xn, or data. And what we are interested in is knowing how likely a parameter, theta, that is assumed to give rise to the law, right? That gave rise to the data, is explaining the observation in some sense. Right? How likely is this parameter for what we saw? That's basically the idea. And so the parameter, of course, lives in the parameter space, this bold theta, right? So for Bernoulli, this is the unit interval. For exponential, it's the positive half line, right? For uniform theta 1, theta 2, what is it? Right? So for this random variable, so what is the parameter space?
0 to 1.
So this guy is, this is this distribution, right? Theta 1, theta 2. It's continuous distribution, right? It has density 1 divided by theta 2 minus theta 1, right? And it jumps there, it's 0 here, and so on. Okay, this guy. So what is the parameter space? Of course, there are two parameters, and these can be real numbers, right? So let's say theta 1 is here, theta 2 is here. And is this a valid one? Let's say this is 1 and 1. So theta 1 is 1, theta 2 is above theta 1. Because we have a constraint, right? This guy cannot go behind that guy, right? So there's a theta 2 has to be greater than or greater than theta 1. So here is my 45-degree line. Oh, terrible drawing. So for example, I can't have something with, so if I have half and 1, this is okay because theta 1 is half, theta 2 is 1. But I can't have something here, right? So the parameter space is this part of the plane, right? You with me? So this is kind of what you now need to bear in mind when you start working with maximum likelihood estimation, because this likelihood function is going to take a value here and map that to the real line. Okay? So I'll draw the real line this way now. So this is just the real line. That's what we're about to see. And the likelihood function, so this is where thetas live. So this is the theta space. And the likelihood function is, say, L of theta it goes from the parameter space to the real line. And it also depends on the data, okay? So the data x1 through xn. So what it's going to try to do is to say how likely are some parameters for the observation versus other parameters. And we're going to build on this. Okay? So that's the idea. So formally, just recall this is all from before, so you know about independent and identically distributed random variables. Suppose we have x1 through xn that are IID according to this probability mass function or density function if it's continuous, little f of x. We always put semicolon and theta for the PMF to explicitly say there's a dependent parameter theta. What is that? If we have this setting, this independent trials, then the actual data as a vector, right, as an n-tuple, a vector in Rn or point in the data space, has this joint density, right? So the probability mass function of f, x1 blah, 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 semicolon theta, is now the product of the individual probabilities, right? The product, because it's independent, and because it's identical, the f's don't change. That's all it is, which is just this multiplication. So, I mean, this is maybe one of the most important points for this notebook, right? So what that allows us to do is the following. So the likelihood function is that this is how it's defined, capital L sub n. So we subscript it by n because we want to remind ourselves of the sample size, right? The sample size of the data. Because later on we will let n change, okay, and increase. So L sub n of theta is formally like this. There is a theta and the data is there as well, but we just suppress the x's to keep it simple. So it's nothing but the likelihood is a function of the parameter given the observation or the data. It's defined to be proportional, right, to the probability, conditional probability of the data given theta. Okay, so that's why we saw conditional probability before. And then that's it, right? So this is basically the joint probability, the joint density, and we're done. So then this general rule applies. If you have a parametric independent trial model with x1 through xn IID f, then the likelihood of theta is simply the product of the individual PDFs. You just, you know, run through all the endpoints. Okay, but the core idea with the likelihood is this. You know, on the right-hand side, you see this is conditional probability of data given theta. But the likelihood views that conditional probability as a function of theta, right? This is the sort of, it gets now slightly philosophical, right? But it's fine. The philosophy is not too bad because the estimators are going to be asymptotically consistent. They have all these nice properties I mentioned before. So if the model were true, with n going to infinity, estimators, things that are trying to guess the true parameter, will actually get closer and closer to the true parameter as we get more and more observations. So that'll happen. So it's not a bad philosophy, you know. So the likelihood function for the Bernoulli theta random variable is what we're going to get into in detail now. But what I'm going to do now is to prepare you for this sort of simulation. So we're going to play this weird game. So there is actually a hidden code here. If you click it, you'll see it, but don't click it. You know, otherwise it's going to defeat the point, right? Later on, we'll see real data, but it's very important to do simulations to test that your estimator is making sense on completely simply simulated data. Because if it doesn't recover simulation, then it's probably some bug in the code. So you can go here and run this cell, okay? So now I ran some hidden code, right? It's not too bad. So there's something here that is actually simulating samples for me. And it produced this, it has this function Bernoulli sample from secret data and samples. So let's pretend that we don't see it. And then this is the general procedure. I put this all again because I will give you a different probability mass function maybe in the assignment or exam. And you'll have to work through this mechanics yourself, either by hand or later on symbolically. So that's our mass function. The joint density is just products of them, so it's just loss of exponents, and it's all explained in detail. You can follow. Oh yeah, it's fine. This is bad later. So this is theta to the power of this, 1 minus theta to the power of this. Okay. So so now, what you notice from this expression is that the summation as I goes from 1 through n of xi is appearing twice. So we can just make this simply called T sub n. T sub n is just the sample sum, right? So what is that? That's a statistic, right? Statistic is a function of the data. So now we can express the likelihood function, right? L sub n as simply theta to the Tn times 1 minus theta to the n minus Tn. So we just simplify that expression to this. So now what is the point of this? First of all, this is much simpler. Second of all, there is a huge saving in the information content. Because, if you look at it that way, as a function of the n tuple, the full data, then, for every data point, so the data space is 0, 1 to the n, right? It's all binary sequences of length n. That's a lot, 2 to the n points. So, but then if you actually do the statistic Tn, you will see it's just numbers between 0, 1, 2, 3 up to n, right? All the different sums of zeros and ones. So now we have a huge compression, right? So the statistic T sub n takes the data and just goes from this space to a space with only n plus 1 elements, from 2 to the n to n plus 1. So later on, this notion is called sufficiency. You will see this maybe in another advanced course. But the main idea here is that statistics can be very clever sometimes if you know what you're doing with a particular model. And in this case, all the information in the data, in the n tuple, is completely preserved by the sum. That's what we will see because, well, that's what we already saw, because the likelihood only depends on the sum. Okay. So anyway, this is just a, so, if you want to get quickly after my blabber, this will help. It's the summary. If you see this. So we have some actual observations or data points, x1 through xn, little x's. So little x's are a realization of the x-valued random variable, right? So we say random variables have values in the space they live in, right? So x-valued or r-valued is the real valued random variable. We've seen little examples in the assignment 2 already, right? Where we started using generators to generate all words from an alphabet, right? You can have a uniform distribution on that space. Then you can say these are, random variables living on that space. So formally, the observed data is a realization of this random variable. And then our model is we have MID theta, Bernoulli theta trials. And they have the joint density like this. We've seen all these definitions. And the joint density goes from the data space to Rn. And then, and corresponding to this, we have a realization of our statistic. So this is very important. When we go into tests, these statistics will become special. The statistic called test statistics. The statistic is just a function of the data. Right? In this case, it's just the sum. That's going from the data space to this space. And the realization of capital T n is little tn, just like realization of capital X is little x. And finally, we can express the likelihood function like this. Okay, so these are the main points so far. So of course, we can use Sage Math Python to get T sub n from the Bernoulli sample from our secret simulation we did, but we don't know what the true theta is that gave rise to the data. So we call the true theta in the model theta star, right? So this is the gain. So there is, so let's make this concrete for this example. So this was for theta 1, theta 2, uniform. So in the Bernoulli problem, so we have x1 through xn, IID, Bernoulli theta. So this is the model. There is some theta star, we don't know. It's some point in interval in the parameter space, right? So our game is, we have an observation, little x1 through little xn. Somebody gave us the sample. That's what's coming from that hidden cell. So our job is to take the sample and come up with some quantity, something we will call the estimator, which is capital theta hat. So then that'll take this and it will give us an output, little theta sub n hat. So this thing is called the estimator, and this is its estimate. So this is the realization. Okay? So that's exactly where we're going to go. And to cut the story really short, theta and hat, when this is defined to be equal to the arg max of theta in the parameter space of the likelihood function, then we call this the maximum likelihood estimator. This is the main punchline for today. We will revisit this rest of the lectures as well. Does anyone know what argmax is? You know what max is? So argmax stands for argument. Argument is what? This is the argument to the function, right? This is the argument. Argument to the whatever function comes after it, right? To this function that maximizes it. So in a picture, if I have a function like this, and say this is my L sub n of theta, and this is my theta space, right? 0, 1, for this Bernoulli problem. Then where this function reaches the highest point, so this is the argmax. So for us, this is the argmax of little theta and capital theta of L sub n of theta. Okay, so we'll see all this in detail. And what the maximum likelihood estimator says, it's all in the word, right? It is the estimator that maximizes the likelihood function. That's all. Okay. So, so let's write a little likelihood function now. We worked it out by hand, or for problems later, you can do it symbolically. So then I'm just writing a little slightly robust function, because some of you in the last problem in assignment 1 were sloppy about edge cases, but then I just gave everyone full points, right? But you want to be careful about the edge cases, right? You know, if the user passes in something that's not well defined and things like this. But this is not a computer science course, so I will not, you know. But we are beginning to get into slightly more complicated things, so the way you code functions will start affecting your interpretation of the mathematics. So there's a little U try below. So all I'm doing is just one crucial point here is I do MPFR theta. Remember, this is the reason why we got into RR, which is the multi-precision floating point real arithmetic in Sage Math. Because if you do it in Python floats, you can replace it and see what happens. It won't work. Okay? So we need to we need a lot of precision when we keep increasing n downstairs later on. Okay. So if we do MPFR theta as RR of theta, so we can get arbitrarily high precision up to how much memory we have, and then we can get the return value to be MPFR theta raised to the t statistic. Well, this is the t, you know. This is the t sub n that we're passing in, not the t test statistic in one word level. And then 1 minus theta to the n minus t. So it's just implementing the function. So yeah, I mean, I have done some, not just me, you know, this is important for really applied statistics, okay? Okay, so this is just to see if you can come up with your own version of this. spend a little time. So now I'm going to actually take my Bernoulli sample, 0. So I'm going to create little examples now. So I'm saying, okay, suppose what if I only observe one tail, right? 1, 0. That's my sample size is 1. My Tn is also 0, right? So then I can apply this to my, so now I want to evaluate the likelihood function at 0. Okay, so I say what is the likelihood of Bernoulli, and then try theta 0 and Tn. Right? So that's just, I'm just plugging in 0, 1, and 0. So, well, that's just 1. So now the idea is I want you to kind of now think about just building this thing little by little for Bernoulli, okay? So now I'm saying try theta is 1, okay? And we just have, instead of tail, now we're observing a heads, okay? What is the likelihood? So now the likelihood is going to be 0 if we set the theta we're trying to evaluate on to be 1, okay? So I mean, this is maybe too easy, but so when theta is half, we get this, but we can just do this on a loop. So if we observe 1, the likelihood of theta is 0. You know, likelihood that for the theta value 0 is 0, 0.2 is 0.2, and so on. So if you guys see a pattern, yeah. So you basically have these nice sword multiplications. You'll see soon. So you can do a list comprehension. And this is just a recall on A range for array range before we've seen in NumPy. So, and then the small Bernoulli sample, now we're increasing it to 0 and 1. So 1 tail, 1 head, sample size 2. And then my Tn is 1, right? And then once again, it's slightly more interesting, right? So now what we saw with in those little examples was this one, SB varied theta, and this one. So when we have only one observation and it's 0, the likelihood function is 1 minus theta. Yes, this is theta. And when we have one observation of x1 is 1, the likelihood function is theta. When we have two observations, these two things are being multiplied, right? That's what I mean by sword fights. Right? So basically, it's really just that, right? It's just a quadratic game between number of ones and zeros, right? So this thing quickly generalizes. So there you go. So now we have two samples. The point to note is this, right? When we have head and tail and head, you see the likelihood shape is the same. Why? Yes, the functions are the same, but why? What is common to 1, 0 and 0, 1 in terms of the likelihood function? How is the likelihood function seeing the data? Is it seeing 1, 0 or 0, 1? It's only seeing the sum, right? The statistic Tn. Tn is 1 plus 0 or 0 plus 1. So Tn doesn't change, right? So that's what and that's the whole point of sufficiency and stuff. So when this gets larger and larger, right, the likelihood function is only going to depend on the number of possible values this T sub n can take, the sum can take, right? So that's just between 0, 1, 2, all the way to n, right? Because all the data points are zeros, which is sum is 0. All the data points are 1, sum is n, or somewhere in between, right? So I might have an assignment. See, I gave you guys the word problem on the alphabet set to kind of jazz into this, but you see, because you can actually look at the likelihood function formally for certain problems, because the entire statistic, not the data space, but the statistics for a particular model will be very small. Maybe just say, in this case, it's just n plus 1, right? The number of samples plus 1. But if it's that small, then you can do some heavy-duty maths on it. And that's done a lot. This area is called algebraic statistics. Anyway, oh shoot. We'll start 2 minutes late. Sorry. You guys should say, Raz, time's up.